All right, let's go ahead and talk about matrix algebra. Today is the 26th, 27th, who knows? 27th, all right. And this Co-17B. Sure, let's start off with some matrices. So here are some 2x2 matrices. Oh, I should wait. Oh, I guess I should wait a minute. Oh, fine, we'll just start. It's okay. I should wait a minute, but I'm not going to. So here are some matrices. When I read this matrix, I read it rows first. So I would, if I was reading this out loud, I would read it as 2, 1, -3, 5. And the matrix B, the 2x2 matrix, is going to be 4, 0, 1, 3. And the 2x2 matrix, oh, sorry, the 2x3 matrix C is going to be 6, 1, 2, -1, 0, 1. So just as some notes here, right? This is a 2x3 matrix. 2 rows, 3 columns. If at any point you have a question, you know you can ask it. All right, so let's add some matrices. Let's do A plus B. Well, A plus B is going to be 2, 1, -3, 5 plus 4, 0, 1, 3. And just like with vectors, when you add matrices together, you add the corresponding components together. So I'm going to get 2 plus 4 in the first row, first column. I'm going to get 1 plus 0 in the first row, second column. I'm going to get -3 plus 1 in the second row, first column. I'm going to get 5 plus 3 in the second row, second column. Whenever you're referring to a row / column, we almost always say the row first and the column second. So this is the second row, first column entry right there that I'm pointing at. And this would just be 6, 1, -2, 8. No big deal. Let's do another one. Let's make it a little bit more interesting. Let's say we wanted to find 3a minus 2b. Well, scalar. So I will point out matrices work a lot like vectors in the adding and subtracting them together and the multiplying them by scalars. If you multiply a matrix by a scalar, you're just going to multiply each entry by that scalar. So when I write 3a, I'm going to do 3 times 2, 1, -3, 5 minus 2 times 4, 0, 1, 3, which is going to equal 6, 3, -9, 15, just multiplying each entry by 3. And here you could either multiply everything by -2 and write plus whatever you get. I would probably keep the minus sign out in front and just multiply each entry by +2. So you get 8, 0, 2, 6. And now I'm going to subtract. 6 minus 8 is -2. 3 minus 0 is 3. -9 minus 2 is -11. 15 minus 6 is 9. There's your resulting 2x2 matrix. What about A plus C? Can't do it. Matrices have to be the same size, meaning they have to have the same number of rows and columns to be able to be added or subtracted together. So not possible. A is 2x2 and C is 2x3. And they're different sizes. All right. Interesting. Sure. Let's do some matrix multiplication. Yeah, multiplication? Sure, multiplication. So let's talk about A times B. So we're going to write that as the matrix A, which is 2, 1, -3, 5, times the matrix B, which is 4, 0, 1, 3. And this is why we talked about the dot product. Because when you multiply matrices together, you are dotting rows of the first matrix with columns of the second matrix. So we're going to do this first row dotted with this first column. So we're going to get 2 times 4 plus 1 times 1. That's our, oh, look, check this out. This is kind of neat. When you multiply the first, or sorry, I'm going to say multiply accidentally a few times here, because when you say you multiply a row by a column, everyone knows you mean you're dotting them together. But bear with me if I say multiply when I should say dot. When I dot the first row with the first column, I get the entry that's in the first row and the first column. When I dot the first row with the second column, I get the entry that's in the first row and the second column. 2 times 0 plus 1 times 3. When I dot the second row with the first column, I get the thing that goes in the second row in the first column. Negative 3 times 4 plus 5 times 0. And finally, when I do the second row dotted with the second column, I get the thing that goes in the second row in the second column. Negative 3 times 0 plus 5 times 3. And then doing the math, we get 8 plus 1, which is 9. We get 0 plus 3, which is 3. We get negative 12 plus 0. And we get 0 plus 15. And that is A times B. I really do like to think of that multiplication the way I was just saying. When you multiply when you dot a row of the first matrix with a column of the second matrix, it ends up in the place that is whatever number column, whatever number row of the resulting matrix. It's kind of cool. Matrices, let's not say that yet, Jim. Let's multiply the opposite order. B times A. So we have the matrix 4, 0, 1, 3. And I want you all to do this one on your own. You can write as much or as little as you want. I would encourage you to get good at multiplying or dotting that by that. Yeah, what's up?
Why is it for the, I guess the first column, first row, no, second row in the first column, why is it
Oh, because I made a mistake. Thank you. Thank you. Negative 3 times 5 plus 4 times, sorry, negative 3 times 4 plus 5 times 1. Ugh, terrible. Which would have been, we had negative 12 plus 5, which is negative 7. If you see something, say something. If you see me making a mistake, please let me know, because I don't want to make mistakes. So there's our A times B. I want you all to find B times A, and it's probably good to write it out in case you might make a mistake like me. All right, let's see what we've got here. So there's what the answer should be, just kind of trying to do it in my head. But let's actually write it out. So I'm doing my first row dotted with my first column. I get 4 times 2 plus 0 times negative 3. Seems a little silly to write 0 times anything, but it's good to still see what's happening here. First row, second column, we get 4 times 1 plus 0 times 5. Second row, first column, 1 times 2 plus 3 times negative 3. And second row, second column, 1 times 1 plus 3 times 5. You might notice that if you keep the order that you're multiplying things in the same, in my first row here, the first part is 4 is there and 0 is there. In my first row here, or my second row here, the first part is 1s and 3s, and then the same kind of thing happens in the columns. In the first column, I have 2s in the second spot and -3s. And in the second column, 1s in the second spot and 5s. That is not coincidence because of how the matrix multiplication works. Cool. Let's look at something else, which I think is noteworthy. Actually, importantly, before I say more, notice not the same. A times B does not equal B times A. And that is probably one of the most important facts about matrix multiplication, is that matrix multiplication, unlike regular number multiplication, is not commutative, which is the word we use to say you can't multiply things in the opposite order and get the same result. So matrix multiplication does not commute. Yeah. I will say though, matrices don't have to be the same size to be multiplied together. They just have to have the same inner dimensions. So what I mean by that is, if I asked you to find, say, let's say A times C, where A is a 2x2 matrix and C was a 2x3 matrix, that's going to work out because the inner dimensions, the second two on the A and the first two on the C, those match. Let me show you. So the matrix A is the matrix 2, 1, -3, 5. And the matrix C was, I forgot what it was. I'm sure I've written it down somewhere over here. Was 6, 1. Oh, did I use the same matrices? Did I actually have it here? Let me double check. Sometimes I change things just to be, no, I did not choose them. 6, 1, 2, -1, 0, 1. Here's how you can tell if it's going to work or not, if things match up. So if I take the first row of A and dot it with the first column of C, do I have the right numbers of things? Oh, I do. I have 2 things there to go with the 2 things there. So it's going to work out just fine. Because the number of columns in A is the same as the number of rows in C. And that's what matters. The number of columns in the first one matching the number of rows in the second one. So when we do this, our 1, 1 entry is going to be 2 times 6 plus 1 times -1. And then first row, second column, 2 times 1 plus 1 times 0. And then first row, third column, 2 times 2 plus 1 times 1. And then second row, first column, -3 times 6 plus 5 times -1. Second row, second column, -3 times 1 plus 5 times 0. And second row, third column, -3 times 2 plus 5 times 1. And if we simplify, we get 12 minus 1, we get 2 plus 0, we get 4 plus 1, and we get -18 minus 5, which is -23. We get -3 plus 0, and we get -6 plus 5. So there's your resulting 2x3 matrix. Also, fun fact, the outer dimensions are the dimensions of the result, the dimensions of the product. This is not super duper important, as most of your matrix experience in calculus is going to consist just of dealing with 2x2 matrices, but it is good to at least talk about what's going on here. The other thing I want to say here is that if I tried to calculate C times A, no dice. If I write this out, C is 6, 1, 2, -1, 0, 1, and A is 2, 1, -3, 5. And look what happens. When I try to do the first row of C dotted with the first column of A, there's not enough things, or there's too many things, whichever way you want to see it. 6 times 2 plus 1 times -3 plus 2 times, there isn't anything for 2 to multiply by. So the number of things here have to match the number of things here for these to be able to multiply together. And they don't. Not defined. And again, it's because C is a 2x3 matrix, A is a 2x2 matrix, and the inner dimensions are not matching up. And if those inner dimensions don't match, the multiplication doesn't work. Cool. What else to say about these matrices? Ah, yes, the transpose. Let me write down A, B, and C again so we have them all. Once again, A is 2, 1, negative 3, 5. B is 4, 0, 1, 3. And C is 6, 1, 2, negative 0, 1. All right, so what does it mean when we do the transpose of a matrix? There's a lot of things you could say. I like to think of either you're flipping it along the main diagonal. Or what's the main diagonal? This. That's a bad. That's bad. Well, it's not that bad. Okay, so a couple of things here. These two matrices, we call these square matrices because the number of rows and the number of columns are the same. So these are square matrices. They're not cool. They're squares. This is not a square matrix, right? It's the dimensions of the number of rows, number of columns are not the same. So this is not square. For a square matrix, we have something that we call the main diagonal. So square matrices. Square matrices have a main diagonal. And it's literally just all the entries where the number, the row number, and the column number are the same. So, which consists of, sorry, my words here are not the best, which consists of the entries where the row number and column number are the same. And there's a lot of words to get at the fact that for A, we would say the main diagonal was 2, 5. For B, the main diagonal was 4, 3. That's it. When you're talking about the main diagonal, you're just starting at the upper left-hand corner, going down to the lower right-hand corner. So if I made up another matrix, say D equal to 4, 1, 0, 3, 2, 0, 6, 5, 3, 9, 8, 7, negative 4, 1, 2, 6. The main diagonal is 4, 0, 8, 6. There's your main diagonal. The reason I mention this is because it gets referred to a lot. We talk about things being above or below the main diagonal. And no, that's kind of, yeah, we'll get there. On the other hand, for this matrix here, C, which is not square, we don't talk about it having a main diagonal. Okay. Now back to what I was saying. For the transpose matrices, find the transpose, but people sometimes write with the prime. Most people like to write transpose the following way. I would write a transpose like that. Some people write it with a C sometimes. Yeah, sometimes with a C, sometimes with a prime. I don't know, does this look familiar to everybody? Or I see, if this has been talked about, does this look familiar? Uses what? That's a different thing. That's the inverse matrix, which we're going to talk about, but that is a different thing than the transpose matrix. So let me show you what the transpose is, and we'll talk about the inverse today as well. The transpose, here's what I would say. Rows become columns and columns become rows. So rows and columns interchange. The first row is now the first column. The second row is now the second column. Or if you want to say it the other way, the first column is now the first row. The second column is now the second row. Some people like to imagine this as literally taking the matrix and flipping it across the main diagonal. If I wanted to be super annoying, I could say that D transpose, the transpose of the matrix D here, is I'm just gonna, for me, it's easiest to look at the row and write it as a column. So my row is 4103, my column is 4103. My second row is 2065, my second column is 2065. Third row, 3987, third column, 3987. Fourth row, fourth column. To me, that is the easiest way to transpose a matrix. Just read the columns and write them down as rows. or read the rows as write them down as columns, whichever way makes more sense to you. It's the same thing. But you can kind of see how it looks like we're taking that matrix and we're flipping it across the diagonal so that these two things interchange places and these interchange places and these interchange and these interchange. That is another way people sometimes like to imagine it, although it's not as easy to see what's happening that way personally. So there's A transpose. B transpose is going to be 4, 0 as a column, 1, 3 as a column. And then finally, C transpose is going to be a different dimension. C transpose, instead of being 2 by 3, is going to be 3 by 2. The dimensions always interchange when you have the transpose of a matrix. So C transpose is going to be the column 6, 1, 2, and the second column is going to be -1, 0, 1. So the transpose matrices, it's really not a hard thing to do. Just take what you've got and make the rows into columns and the columns into rows. And then sometimes we like to do things with the transpose, like maybe we want to multiply the matrix by its own transpose. Let's take C and multiply it together. C transpose by C. Oh, what letter am I on here? Sorry. Let's just start over. We don't need to, no, that's fine. We'll continue with the letters. H, letter H. Let's find, yeah, C transpose times C. So C transpose is going to be this matrix, 6, -1, 0, 2, 1. And C is the transpose of that, which is 6, 1, 2, -1, 0, 1. All right, let's multiply these together. Let me ask you all. Well, think about this. If this is a 3 by 2 matrix, and this is a 2 by 3 matrix, what dimension or size is the product going to be? Is it going to be 3 by 3 or is it going to be 2 by 2? 3 by 3, because it's the outer dimensions. The inner dimensions have to match. The outer dimensions are what you're left with. Let's do it. It's also good to know how big it's going to be so that we can prepare for that. So let's see, 6 times 6 plus -1 times -1. And then 6 times 1 plus -1 times 0. Again, no one expects you to write all this when you actually do the matrix multiplication, but I'm writing it so you're seeing it. 6 times 2 plus -1 times 1. Second row, 1. So the second row should be pretty easy, right? 1 times 6 plus 0 times the next thing. And then 1 times 1 plus 0 times 0. And then 1 times 2 plus 0 times 1. And finally, third row, first column, we get a 2 times 6 and a 1 times -1. And then a 2 times 1 plus a 1 times 0. And then a 2 times 2 plus a 1 times 1. All right. And then we see what we got. Let's see here. 36 plus 1 is 37. 6 plus 0. 12 minus 1. 6. 1. 2. 12 minus 1 is 11. 2 plus 0 is 2. 4 plus 1 is 5. Ooh, here's a fun question. Let's call this matrix E. What is the transpose of E? Did I write down the transpose or the same matrix I started with? I mean, it's not an or question. It's really, the answer is both. I wrote down the matrix that is the transpose that happens to be the same as the matrix I started with. This is an example of what's called a symmetric matrix. If a matrix is equal to its own transpose, it is called symmetric. You probably don't need to know that though, but it seemed like I might as well say it since we're there. And it is true that if you ever multiply a matrix by its own transpose, you will get a symmetric matrix. So if we actually go the other way, we do C times C transpose, which is going to be 6, 1, 2, negative 1, 0, 1 times 6, negative 1, 1, 0, 2, 1. All right, let's do this one without writing all the stuff because I don't have much room here. 612 times 612 dotted with 612 is going to be 36 plus 1 plus 4, which is 41. 612 dotted with negative 101 is going to be negative. So watch how I'm doing this. I'm pointing to the things while I'm thinking negative 6 plus 0 plus 2. Negative 6 plus 0 plus 2 is negative 4. Same thing for this next one. The second row dotted with the first column is going to be negative 6 plus 0 plus 2. And finally, the second row dotted with the second column is 1 plus 0 plus 1. Just 2. Oh, look, that matrix is also symmetric. If you take its transpose, it doesn't change it at all. It's kind of neat. Yeah. Okay. What is an identity matrix? Well, technically this should have a slightly more accurate name. But an identity matrix is a matrix. I think in Goldsmith's class he said it was like nothing, which I take issue with. It's like I would say it's better described as being like the number 1. Because what's special about the number 1 is when you multiply by the number 1, it doesn't change anything. So it's kind of like you've done nothing. But there's another thing that's also kind of like nothing, the number 0. If you add 0 to something else, it doesn't change it either. So what I would say is an identity matrix is the multiplicative identity. And what it means is, I know we haven't written it down, but we're about to. If you multiply any matrix by an identity matrix, it won't change it. So if we multiply a matrix, let's say A, by the appropriate sized identity matrix, appropriate, yeah, I can spell, sized identity matrix, which we're going to label as capital I. Then we get A back. That is A times I, or I times A, should equal A. That's what's special about the identity. Just like the number 1, 1 times 5 equals 5 times 1 equals 5. Okay, it's a lot of buildup for not having said what it is yet. So here is what an identity matrix always is. Identity matrix is a square matrix that has 1s on the main diagonal and 0s everywhere else. So the 2 by 2 matrix I2 is 1, 0, 0, 1. The 3 by 3 matrix I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. When they get big enough, people get lazy and they just start writing 1s on the diagonal. And they write a big old 0 in the. So like if I was going to write like I7, I would probably write it like this. I probably wouldn't even write all the 1s. Probably write 1, 1, dot, 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 1, and then a big 0, 0, and a big 0 there. If someone writes that, that's what they mean. They mean 1s on the diagonal and 0s everywhere else. I could actually write it out. 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Right? This is terrible though. Nobody wants to do this. Plus, eventually it gets hard to make sure all your zeros line up. And I didn't make my matrix big enough See, this is why you don't do it this way. There. Nobody's gonna do that. Again, we're also not gonna deal with matrices that large in this class, so it's not that big a deal. But I will just tell you, if someone's trying to represent a larger identity matrix, they probably will write it this way. So for example, if I take this 2 by 2 matrix and multiply it by my matrix A, which was, I don't remember what it was. I'm just gonna make it a new A. Let's say A is 6, 2, 7, 9. Well, check this out. A times I, which is 6, 2, 7, 9 times 1, 0, 0, 1 is equal to, let's see, 6, 2 dotted with 1, 0 is going to be 6 times 1 plus 2 times 0. 6, 2 dotted with 0, 1 is going to be 6 times 0 plus 2 times 1. 7, 9 dotted with 1, 0 is going to be 7 times 1 plus 9 times 0. And 7, 9 dotted with 0, 1 is going to be 7 times 0 plus 9 times 1. Which is A. And unlike most matrix multiplication, here order actually doesn't matter. The identity matrix is a matrix that is commutative with other matrices. So if we did I times A instead, and we did 1, 0, 0, 1 times 6, 2, 7, 9, we're still going to get the same result. 1, 0 dotted with 6, 7 is going to give you 6 plus 0. 1, 0 dotted with 2, 9 is going to give you 2 plus 0. 0, 1 dotted with 6, 7 is going to give you 0 plus 7. 0, 1 dotted with 2, 9 is going to give you 0 plus 9. Same result. Sometimes something funky happens though, and the matrix that's the identity matrix for one multiplication is not the same for the other. What do I mean? Let's say we had a different 2 by 3 matrix. Let's say we've got B equal to my favorite 2 by 3 matrix, 1, 2, 3, 4, 5, 6. So now if you want to multiply B on the left by an identity matrix, I times B is going to equal 1, 0, 0, 1 times the matrix 1, 2, 3, 4, 5, 6. And I could do the multiplication, but we know what's going to happen. We're going to end up with B. We're going to get 1, 2, 3, 0 plus 4, 0 plus 5, 0 plus 6. So when you write down an identity matrix times another matrix, the assumption is that you are choosing the identity matrix of the correct size, so that you're not making some sort of impossible multiplication. If I were to write this the other way, meaning B times I would write this as my matrix B 1, 2, 3, 4, 5, 6 times the correct size identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. The unsaid implication here being that this one, of course, had to be a 2 by 2 identity matrix, so that it's the right size to multiply B on the left. This one has to be a 3 by 3 identity matrix to be the right size to multiply B on the right. Yeah. Yes, I1 exists as well. I1 is just, it's not the number 1. I1 is the matrix consisting of just a 1. But it is a matrix, not a number. But it acts a lot like just a regular number. Yeah, good question. And so here, if you multiply it out, you literally get the same thing, right? 1, 2, 3 dotted with that is going to be 1. 1, 2, 3 dotted with that is going to be 2. 1, 2, 3 dotted with that is going to be 3. 4, 5, 6 dotted with that. 4, 5, 6 dotted with that. 4, 5, 6 dotted with that. So the identity matrix acts like the number 1 in that it has the same sort of multiplicative property. And just so that we're all on the same page, the 0 matrix is what it sounds like. It's a matrix of all zeros. It's a matrix of whatever size of all zeros. So if I wrote like the 0, 2 by 4 matrix, that would be the matrix that had zeros in all 8 of the 2 by 4 entries. And just like the regular number 0, the 0 matrix is the additive identity. If you add the 0 matrix to any other matrix, it won't change it. if I take my matrix B there, plus the 0 matrix, that's a 2 by 3 matrix, I'm going to get 1, 2, 3, 4, 5, 6, plus 0, 0, 0, 0, 0, 0. Not exciting at all. It's just what we started with. 1, 2, 3, 1 plus 0, 2 plus 0, 3 plus 0, 4 plus 0, 5 plus 0, 6 plus 0. So yeah, but worth mentioning because it does come up sometimes. Yeah, it comes up. Yeah, sure, maybe. Maybe. Okay. What time is it? Oh, we got enough time. Cool. Let's continue on. So here's kind of why we're talking about any of this. Again, I know I said the big goal is to talk about like eigenvectors, eigenvalues, but the reason we're actually going to talk about those is because next quarter you're going to want to be solving systems of equations that look kind of like, but not exactly like this. We would love to be able to solve 2x plus y equal to 7 and x plus 3y equal to 4. And yes, I know we could solve this like the old way where you maybe solve for y and plug into the other equation, but that's not going to be an option in the future because we're going to have other things. So there's another way of solving something like this, which is to write it as a matrix equation. So we're going to write this as a matrix equation. Check it out. We're going to have what people typically call the coefficient matrix, which is literally just the coefficients of x in the first column, the coefficients of y in the second column, the coefficients for the first equation in the first row, the coefficients for the second equation in the second row. So my coefficients in the first row are going to be 2 and 1, and the second row are going to be 1 and 3. My vector of variables, x times y, equal to what it's supposed to equal, the vector 7, 4. Now check that out. If we actually wrote this out, we would have 2 times x plus 1 times y equals 7, and 1 times x plus 3 times y equals 4. It's literally the same as what we've written up here, just a more compact way of writing this. So what can we do? Well, I would love to be able to find x and y here. Now, sadly, there isn't an operation of matrix division. You cannot divide a matrix by another matrix. Some matrices aren't divisible, for lack of a better word. Really, the word I'm actually looking for is some matrices aren't invertible. Many matrices have an inverse. This one does. Some don't, which is annoying, but we'll talk about that maybe. So the question becomes, how do you find the inverse of a matrix? Well, for 2 by 2 matrices, it's really easy. For other matrices, for larger matrices that are 3 by 3 or 4 by 4 or any square matrix, because only square matrices have inverses. But for any square matrix that's larger, the process is there, but it's much more involved. I don't think you'll be asked to do. Yeah, I know some of your teachers might ask you to do the inverse of a 3 by 3 this quarter. Let me know if that's the case. We'll talk about it. But I'm going to go with the assumption that we're all just inverting 2 by 2 matrices. So here's the way you invert it. If this is your matrix A, then A inverse is equal to the following. So here's what I'm going to say. First, you're going to switch the diagonal entries. So 2 and 3 switch places. And then the off diagonal entries change signs. So if they were positive, they're negative. If they were negative, they're positive. If it's one, right. So since I have a positive one, it's going to be a negative one. A positive one is going to be a negative one. Now there's one more thing I need. In fact, we'll come back here. We're going to fix this in a second. But here's the point. When you multiply a matrix by its inverse, they should multiply to the identity matrix. Let's see if that works so far. If I take what I think is the inverse over here, which I know it's not, but I'm pretending like it is. If we multiply the inverse by the original matrix, let's see what we get. See, 3 times 2 plus -1 times 1 is 6 minus 1, which is 5. 3 times 1 plus negative 1 times 3 is 3 minus 3, which is 0. Negative 1 times 2 plus 2 times 1 is negative 2 plus 2, which is 0. And negative 1 times 1 plus 2 times 3 is negative 1 plus 6, which is 5. And if I just multiply this entire matrix by what, I would get the identity. Or divided by what, if you prefer. What do I want in the diagonals there? I don't want 5s. I want 1s. So what do I need to divide by? Divide by 5 or multiply by 1/5. Now we'll talk about where that came from in just a second. But so I want to point out 1/5 times this matrix is the identity matrix 1, 0, 0, 1. We're just multiplying every entry by 1/5. So where is that 1/5 coming from? It's coming from 1 over the determinant of A. The determinant of A, which we'll talk more about in a second, is the product of the diagonals minus the product of the off diagonals, which is exactly 1/5 times the matrix 3, negative 1, negative 1, 2. I would leave it like this. If you want, you could distribute the 1/5 and write it as 3/5, negative 1/5, negative 1/5, 2/5. There is no good reason to do this. You should not do this. Don't write this down. I mean, you can. I'm not going to stop you, but this is much better to write it like this. It's much easier to deal with if you write it like this. Okay, so here's the point. We were trying to solve, let's call this the vector X. Let's call this the vector B. Fairly standard notation to call things that. So what we did was we said, well, we were trying, I'm going to cover this up for a minute. Don't worry, it'll come back. We were trying to solve A times X equal to B. And what we're going to do, instead of dividing both sides by the matrix A, since we can't, we're going to multiply both sides by the inverse of A. Watch for just a second. When we do this, look what happens. You get A inverse times A times X equal to A inverse times B. All right, here's the big thing you need to know. What's A inverse times A? Well, let's see. When we multiplied the matrix A by A inverse, what do we end up with? What do we end up with? The identity. And that is always true. When you multiply a matrix by its inverse, if it exists, not every matrix has an inverse, but if it does, and you multiply them together, it always multiplies to the identity. That is the way the inverse is defined. So look, A inverse times A is just the identity. In this case, the 2 by 2 identity. But I'll remind you that when you multiply the identity matrix by any other matrix or vector, you get that vector or matrix back. So the identity times anything is just the thing you're multiplying by. So our solution is going to be that X, the thing we're trying to find, which is really XY, the vector, is going to equal A inverse, which was 1/5 times 3, negative 1, negative 1, 2, times 7, 4. And now we can actually do the multiplication. Let's see what happens. So that's going to be 1/5 times 3 times 7 plus negative 1 times 4 is 21 minus 4, which is 17. And negative 7 plus 8 is going to be positive 1. And then I would probably distribute here. So my solution to the equation 2x plus y equals 7 and x plus 3y equals 4 is x equals 17/5 and y equals 1/5. Now, was that more work than doing it the more normal way? I don't know, maybe. But that's not the point. The point is we are learning what the inverse is. So let's see a few. Yeah, we got 6 minutes. Let's say a few more things about the inverse here. So for a 2 by 2 matrix, A equal to A, B, C, D. A inverse is equal to 1 divided by AD minus BC. That's the product of the diagonals minus the product of the off diagonals times the matrix where you interchange the diagonals. So D goes there and A goes there. And the off diagonals stay in the same spot, but you change them to the opposite sign of what they were. So it's going to be negative B there and negative C there. Now, this equals this provided that this thing you're dividing by here isn't what? What would be a problem for us to try and divide by? Right, provided that AD minus BC is not equal to 0. So for a 2 by 2 matrix to be invertible, so for a 2 by 2 matrix, A equal to ABCD to be invertible or to have an inverse, you might hear your professor throw around the word non-singular. It means the same thing. If they say something is non-singular, they mean that it has an inverse. The way I think of it, because I used to get really confused by this word, if it's non-singular, it's not single. It has a partner, and its partner is its inverse. So if they say non-singular, it's not single. It has a partner to go with it. It has an inverse. If it is singular, then it does not have an inverse. So to be invertible, the determinant of A, which is equal to the product of the diagonals minus the product of the off diagonals, cannot be equal to 0. And just to go along with that, for A equal to A, B, C, D, the determinant, which is something you'll be taking a lot of next quarter, of A is exactly what we said right there. It is more complicated for 3 by 3 or larger square matrices. So if we have to talk about that, again, I will look out for that in the notes, but you should also let me know. Like if your teacher is talking about taking the determinant of a 3 by 3 matrix or a 4 by 4 matrix, let me know. We can definitely cover that. But it's painful to cover if you don't have to cover it. So we'll avoid it if we can. Let's see here. What time is it? Let's do a minute or 2 here. I could say more things. Yeah, sure. So I feel like there was something that was really on my mind that I saw in the homework, but now I've forgotten what it was. So, oh well, it's too late for that. Is there anything that I'm not saying that you would like me to say in the next couple minutes here? Like, is there something from the homework or from the class that feels like we haven't touched on just yet? I know we haven't talked about eigenvalues and eigenvectors yet, which we're going to get to hopefully this week. I guess that's all the things I can say. Let me look back here and see if there's anything else seems really super important. No, I don't think so. So let me ask you a question. Are these two matrices inverses? How could you tell? Well, one way would be like to do the thing, right? But the easier, in my opinion, easier way to tell is multiply them together. we multiply them, that'll tell us. Let's see, 4 times 1 plus 3 times -1 is 1. 4 times -3 plus 3 times 4 is -12 plus 12. 1 times 1 plus -1 times 1 is 0. 1 times -3 plus 4 times 1 is 1. Yes. Because they multiplied to the identity matrix. And that is literally the definition of an inverse, is you have to multiply it by the other matrix and it has to come out to be the identity. So if A and A inverse exists, then it must be true that A times A inverse is equal to A inverse times A is equal to the identity matrix of whatever appropriate size. All of this talk about inverses and identity matrices is in the context that our matrix must be square. You cannot have an identity matrix that is not square. You cannot have a matrix be invertible or not that is not square. We don't talk about being invertible if it's not square. All right. We'll talk more about matrices on Wednesday. And you all should definitely, if you start talking about finding the determinant of a 3x3 matrix or the inverse of a 3x3 matrix, please let me know. We will talk about it if we need to. It's not that terrible, but it is more terrible than finding the inverse and determinant of a 2x2 matrix. Every what? Well, the identity is just this matrix. I would say every matrix does not have an identity. In fact, so in case, just for one last example, I know I said to go, but let me just point out, here's a matrix 1, 3, 2, 6. This is not invertible. There isn't a matrix you could multiply it by that would end up being the identity. You can either see it by trying to find the inverse and showing and seeing that the determinant is 0. Right, the determinant of A is 1 times 6 minus 3 times 2, which is 0. Or you could actually try finding it. If you multiply this matrix by the supposed identity, and you get 1 times A plus 3 times C, and 1 times B plus 3 times D, and 2 times A plus 6 times C, and 2 times B plus 6 times D, check out what happens. We need this to equal 1, 0, 0, 1. And that is what has to happen for it to be invertible. But here's the problem. If, let's say, if 1B plus 3D equals 0, then B has to equal negative 3D. But then if I jam that back in here, I need 2B plus 6D to equal 1. But I just said B had to be negative 3D. So that means I have 2 times negative 3D plus 6D equal to 1. But negative 6D plus 6D is 0. That's not going to work. So when you have matrices like this, where one row is a multiple of another row, or one column is a multiple of another column, it will not be invertible. You cannot find a matrix to multiply it by where you get this. You always reach some sort of impossibility like that. So not every matrix has an inverse. You're welcome.